In this video, we are going to discuss the behavior of the electric field and of the electric potential across a charged surface. So suppose that we have a surface of any shape with a surface charge density sigma, and sigma does not have to be uniform. It can vary on the surface. And the question we want to answer is, how does the electric field just above the surface and just below the surface are related to each other? We will do this in multiple steps. First, we will look at the component of the electric field that is perpendicular to the surface. But even before we look at this, we're going to take this opportunity to do one more application of Gauss's law. We will do it supposing the plane is infinite and sigma is uniform. So what is the electric field everywhere in space in this situation? After that, we will come back to our boundary case, but first, let's do the infinite and uniform plane and look at the electric field everywhere. So if the plane is perfectly flat, then by symmetry, the electric field has to be perpendicular to the plane. So E will be along n hat, where n hat is the vector normal to the plane. Then we're going to choose a Gaussian surface so that we can calculate the flux of E across that surface. As we discussed already, given the symmetry of the plane, the Gaussian surface that makes sense is a pillbox with a top and bottom surfaces that have area A. Then we can write the flux of E out of this pillbox. The electric field is in the n hat direction, so it is perpendicular to the top and bottom area. The flux through the top and the flux through the bottom are equal, so the integral is 2AE. And note that there is no need to consider the flux through the sides of the pillbox, because in the case of the infinite uniform plane, E is along n hat, so it contributes no flux through the sides, even if the box is very tall. Now we can write Gauss's law. This flux on the closed surface of the pillbox is equal to Q enclosed in that pillbox divided by epsilon naught. And Q enclosed is sigma times the area A. We can simplify the area and we obtain that the electric field is equal to sigma over 2 epsilon naught along n hat. You can see that this value of the electric field does not depend on the distance from the plane. You can be very far from the plane or very close, the electric field is the same. This is only true, of course, because we consider the plane infinite as an example. So suppose we look at this plane from the side. So the red line here in the middle is the infinite plane viewed from the side. Then the black arrows represent the electric field. In this example, I assume the surface charge density is positive, so E is pointing along plus n hat. That makes sense, right? If the plane has positive charges, then the electric field points away from the positive charges. And the electric field is constant. As you move away from the plane, it does not decrease. If instead sigma is negative, then the electric field points in the opposite direction, that is, points towards the negative charges of the plane. But otherwise, it is the same. It does not decrease as you move away, as long as the plane is infinite. You see that in both cases, positive or negative sigma, the direction of the electric field is opposite when you go from one side of the plane to the other. So coming back here, we can add one more observation. The electric field component that is perpendicular to the plane is discontinuous across the charged surface. Keep in mind these two results, and now let's come back to our more general surface charge, which is non-infinite, which can be curved, and non-uniformly charged. Because we don't have the nice symmetry, we will not be able to find the electric field everywhere, but what we can do is look at the electric field very close, just at the boundary. So if sigma is not uniform, you can always choose the area of the pillbox to be very small, so that the charge density sigma is constant over the area. This time, the electric field is not exactly along n hat, so there can be some flux of E through the sides of the pillbox, but you can make the thickness of the box so small that the sides do not contribute any flux. And so we can still use the previous result, but only at the boundary. And we can write that the difference E perpendicular above minus E perpendicular below is equal to sigma over epsilon naught. Now let's look at the parallel component. For the electric field component that is parallel to the plane, we are going to use another property of an electrostatic field, which is that the integral over a closed loop of E dot dl is equal to 0. So we choose a path that has a length L parallel to the plane above the plane, then returns below the plane, same length L, and closes the loop. We also choose an orientation for the integral along the loop. And when doing the integral along the sides, the component that is perpendicular will contribute, but in the limit of epsilon tends to 0, then the sides contribute nothing to the line integral. So again, when we consider the electric field just at the boundary, in the limit of epsilon equal to 0, we only have the contribution from the length L on top and the length L below the surface. So the integral along the loop is 0, gives us that E parallel above times L minus E parallel below times L is equal to 0. The sign difference here comes from the fact that the positive direction for dl is opposite above and below the surface. This relation gives us that the field parallel above and the field parallel below the surface have to be equal. In other words, the parallel component of the electric field is continuous across the charged surface. Only the perpendicular component is discontinuous. If you write these two boundary conditions with vectors, then you have only one condition. The electric field above minus the electric field below as vectors is equal to sigma over epsilon naught along n hat, where n hat is a vector that goes from below to above. So if you know the charge density sigma, then you know the discontinuity of the electric field. And if you know the discontinuity of the electric field, then you know the charge density of the surface. Now, if you don't know the electric field discontinuity, but you know the electric potential, then there is another relation. So remember that we introduced the electric potential such that the difference in potential is equal to minus the integral of E dot dl along a path that connects the 2 points. So applying this to points above and below the surface, V above minus V below is equal to minus the integral from below to above of E dot dl. If dl tends to 0, that is if we look at the difference of electric potential just above and just below the surface, exactly at the boundary, then we obtain that the integral is 0. So V above minus V below is equal to 0. This result means that V is continuous across any boundary, regardless of charges of that surface boundary. What is discontinuous, in fact, is the slope or the derivative or the gradient, to be exact, of the potential. To see this, come back to the discontinuity relation of the electric field. E above minus E below is equal to sigma over epsilon naught n hat, and replace E by minus the gradient of V. Then gradient of V above minus gradient of V below is minus sigma over epsilon naught n hat. That means that only the component of the gradient that is in the direction of n hat is discontinuous. Another way to write this relation is to take the scalar product with n hat on both sides of the equation, you obtain that the variation of V above along n, dV dn above, minus dV dn below is equal to minus sigma over epsilon naught. This notation, partial V over partial n, is the same as the gradient of V dot n hat. And physically, it represents the rate of change in the direction perpendicular to the surface. So we found that V itself is continuous, but its variation in the direction perpendicular to the surface is discontinuous. Coming back to our charged infinite plane viewed from the side, remember the black arrows represent the electric field. Here the charge density sigma is positive, and E is sigma over 2 epsilon naught along n hat. So using that V is minus the integral of E dot dl, you can find that V is minus sigma over 2 epsilon naught z, where z is in the direction perpendicular to the plane. You can check that if you take minus the gradient of this, you get the electric field. And now I'm adding the plot of the electric potential as a function of z. You can see that V is continuous at the boundary, but the variation is discontinuous. You have a positive slope on the left and a negative slope on the right. And if sigma is negative, then the electric field is pointing towards the plane, and the potential, which goes as minus sigma, is now positive. Again, it is continuous at the boundary. Now, in this example of infinite plane, you see that the potential at infinity, very far away from the plane, is infinite. This is an example of a situation where the reference potential is not taken at infinity, but instead it is taken on the plane. V is chosen to be 0 on the plane. So to conclude, we can update our summary of equations for electrostatics. We have already mentioned the relations that we have between the charge density, the electric field, and the electric potential. And now we saw that you have boundary conditions. The electric field is discontinuous across a charged surface. E above minus E below is equal to sigma over epsilon naught along n hat, with n hat from below to above. The electric potential is continuous across any boundary, so V above minus V below equals 0. And partial V above over partial n minus partial V below over partial n is equal to minus sigma over epsilon naught.